everyone. In my lecture series on thermal physics, I have now started with a discussion on thermodynamic potentials. In my last lecture, I had discussed the various thermodynamic potentials, the internal energy, the Helmholtz free energy, enthalpy, and I had started with Gibbs function. So let me continue my lecture from where I had left off. As discussed, what is Gibbs function? Gibbs function is defined as H minus Ts. H is U plus PV, so G is U plus PV minus Ts. If we differentiate both sides, we get dG is equal to dH minus TdS minus SdT. Hence we get dG is equal to TdS plus VdP minus TdS minus SdT. So as you can see, TdS gets cancelled and we are left with dG is equal to VdP minus SdT. Now, if you remember, an equation of this kind in dealing with the Helmholtz free energy, we were able to derive what is the pressure and what is the entropy. So likewise, from this equation we can find out what is the volume and how is the entropy defined. So we get delta G by delta P at constant T is equal to V, and delta G by delta T at constant P is going to be equal to minus of S. So what do we get? We get that for a reversible isothermal and isobaric process, G is equal to constant, dG is equal to 0. Thus, the Gibbs function or the Gibbs potential is also called the isothermal isobaric potential, and the independent variables in this case are temperature and pressure, as you can see very well from the above equations. So this was the basic definitions of the four thermodynamic potentials. Now let us discuss what is the significance of thermodynamic potentials. A mechanical system is said to be in stable equilibrium if the potential energy of the system is minimum. For example, heat flows from higher to lower temperature till equilibrium is achieved. In the last lecture, where I had discussed the transport phenomena, you had seen that the flow of heat from higher to lower temperature to achieve equilibrium leads to a very important phenomena called the thermal conductivity. As the internal energy, enthalpy, Helmholtz free energy and the Gibbs free energy are all energy functions in thermodynamics, they behave similar to potential energy in mechanics. In an isochoric adiabatic process, the internal energy tends to a minimum. In an isobaric adiabatic process, enthalpy tends to a minimum. In an isochoric isothermal process, the Helmholtz free energy tends to a minimum. In an isobaric isothermal process, the Gibbs free energy tends to a minimum. In an isochoric process, remember, volume is a constant. In an isothermal process, temperature is a constant. In an isobaric process, the pressure is a constant, and in an adiabatic process, the entropy is a constant. So thus we can say that the Maxwell's thermodynamic relations, which are very important relations, can be derived from the various thermodynamic potentials. Now here I will mention that the Maxwell's thermodynamical relations can be derived from the first law and the second law also. But the derivation is a little tedious. If we use the thermodynamic potentials, the derivation of the Maxwell's thermodynamic relations is simplified to a large extent. These relations are extremely important to solve various cases or various problems in thermodynamics. They have various applications. So because I am doing the Maxwell's thermodynamic relations in this lecture series for the first time, let me briefly tell you what are the Maxwell's thermodynamic relations. The Maxwell's relations are the relations between the various thermodynamic variables that hold at any equilibrium state of a hydrostatic system. They provide relationships between measurable quantities and those which either cannot be measured or are difficult to measure. By using the Maxwell's relation, we can relate the partial derivatives of thermodynamical properties to each other and calculate changes in these properties as a function of the state variable of the system. You will appreciate this point in a few moments, where I will be showing that how Maxwell's relations are simply partial derivatives of thermodynamical properties related to each other. Let us derive the Maxwell's thermodynamic relations. Now remember, there are 4 thermodynamic relations given by Maxwell. There are 4 thermodynamic potentials and there are 4 Maxwell's relations. So we can easily see that each thermodynamic potential is leading to one Maxwell relation. So how to go ahead? If a relation exists between the variables x, y and z, then z can be expressed in terms of x and y as dz is equal to delta z by delta x at constant y into dx plus delta z by delta y at constant x into dy. Let us represent delta z by delta x at constant y as m and delta z by delta y at constant x is equal to n. So substituting this, what do we get? We get dz is equal to m dx plus n dy. Call this equation 1. Let us partially differentiate m with respect to y and n with respect to x. So what do we get? We get delta m by delta y at constant x is equal to delta square z by delta x delta y and delta n by delta x at constant y is equal to delta square z by delta x delta y. If we see the right hand side of these two equations, they are the same. So what does this mean? This means that delta m by delta y at constant x should be equal to delta n by delta x at constant y. Call this equation 2. This is the condition for exact differential and is applicable to all the thermodynamic potentials, be it U or F or H or G. So this result is applied to the four exact differentials du, df, dh and dg to get the Maxwell's equation. du is going to give me one Maxwell's equation, df the second, dh the third and dg the fourth. So let us now derive the first Maxwell's equation using internal energy. From the first law we have dq is equal to du plus pdv, and from the second law we have dq is equal to tds. If we combine the above two relations, we get tds is equal to du plus pdv, or we can write du is equal to tds minus pdv. If we compare the first equation with the fourth equation, we can see that in equation fourth, m is equal to t and n is equal to minus p, x is equal to s and y is equal to v. If we substitute these variables in equation 2, what do we get? Delta t by delta v at constant s is equal to minus delta p by delta s at constant v. This is the first Maxwell's relation, and you can see it is combining the differential of temperature with the differential of pressure. Now let us derive the second Maxwell's relation. To derive the second Maxwell's relation, we will use the Helmholtz function. By definition, the Helmholtz function f is equal to u minus ts. For an infinitesimal reversible process, we have df is equal to du minus tds minus sdt. From the combined first and second law of thermodynamics, we have tds is equal to du plus pdv. Hence, we can write df as du minus du plus pdv minus sdt. Du gets cancelled and we get df is equal to minus pdv minus sdt. Care should be taken to be careful with the negative signs, and the negative signs should not be missed under any circumstances. Comparing equation 1 with equation 6, we can see that in equation 6, m is equal to minus p, n is equal to minus s, x is v and y is equal to t. If we substitute these variables in equation 2, we get delta p by delta t at constant v is equal to delta s by delta v at constant t. So just let me transpose delta s by delta v on the left hand side and take delta p by delta t on the right hand side. So what do I get? We get delta s by delta v at constant t is equal to delta p by delta t at constant v. This is the second Maxwell's relation, and please take care. T, delta p by delta t is appearing in the denominator on the right hand side, and therefore the left hand side, the constant parameter is t. On the left hand side, in the denominator we have delta v, it means volume. Therefore, on the right hand side, the constant parameter is taken as V or the volume. So you can see that the second relation relates the partial derivative of entropy with respect to volume at constant temperature to the partial derivative of pressure with respect to the temperature at constant volume. Now let us derive the third Maxwell's equation. To derive the third Maxwell's equation or relation, we will use the third thermodynamic potential, that is the enthalpy. As seen in the previous lecture, enthalpy of a system is the total heat energy of a system and is defined as H is equal to U plus PV. If the system undergoes an infinitesimal process, we get dH is equal to du plus pdV plus vdP. From the combined first and the second law of thermodynamics, we have TdS is equal to du plus pdV. Thus, dH is written as TdS plus vdP. Let us now compare equation 1 with equation 8, and what do we get? In equation 8, m is nothing but temperature, n is volume, x, that is the constant variables, are S and y is P. If we substitute these variables in equation 2, we get delta T by delta P at constant S is equal to delta V by delta S at constant P. Constant S means adiabatic process, constant P means isobaric process. Again, you can appreciate the fact that on the right hand side of equation 9, in the denominator we have S, delta S, and therefore on the left hand side as a constant parameter we have S. Likewise, if we concentrate on the left hand side, in the denominator we have delta P, that is the pressure, and on the right hand side the constant parameter is therefore pressure. So one should be very careful in writing the Maxwell's relation correctly. Now let us derive the fourth Maxwell's equation. To derive the fourth Maxwell's relation, we use the Gibbs function. As mentioned earlier, each potential gives rise to one Maxwell relation. So we are now left with the Gibbs function. So we will now use Gibbs function to derive the Maxwell's relation, that is the fourth relation now. By definition, G is equal to H minus Ts. H is the enthalpy, T is the temperature, S is the entropy. For an infinitesimal reversible process, we have dG is equal to dH minus TdS minus SdT. Also, dH is equal to TdS plus VdP. Using this in the previous equation, we get dG is equal to VdP minus SdT. If we now compare equation 1 with 10, we will see that m is nothing but volume V, n is minus S, it means minus of entropy. The constant variables in this case are x equal to P and y equal to T. So if we substitute these variables in equation 2, we get delta V by delta T at constant P is equal to minus delta S by delta P at constant T. Let us just briefly rearrange this equation and we get delta S by delta P at constant T is equal to minus delta V by delta T at constant P. Again you will appreciate that delta T is appearing in the denominator of the right hand side, and therefore on the left hand side we have taken T to be a constant. Likewise, delta P is appearing on the denominator of the left hand side, and therefore on the right hand side we have taken the constant as pressure. To remember the Maxwell relation, we have to remember a simple sentence TV special program taken clockwise along a circle as shown. TVS special program, TVSP. T stands for temperature, V stands for volume, S stands for entropy, and P stands for pressure. To derive or to write down the first relation, we start from T and read anti-clockwise. Whenever we read anti-clockwise, we have to take the negative sign. So we have TPSV. To derive the second relation, we start from S and read clockwise. That is, if we are starting reading clockwise, then the relation has to be positive. So SPTV. This means delta S by delta V is equal to delta P by delta T. To derive the third relation, we start from T and read clockwise, and therefore the third relation is also positive. TVSP. To derive the fourth relation, we start from S and read anti-clockwise. Because we have read anti-clockwise, this relation is negative. SVTP. So you can see and appreciate how easy it is to remember the four Maxwell relations. So this was as far as the derivation of Maxwell relations. Now, why are Maxwell relations so important? Maxwell's relations are very, very important. They help us to derive a number of relations, namely the TDS equations, the energy equations, the Clausius-Clapeyron equations, very, very important. And also, using Maxwell relation, we can find out the various relations that exist between Cp and Cv. So let us discuss each of these applications in detail. These are very important and have applications in real cases also while studying the real gas and the ideal gas. So first application is the TDS equations. To derive the first TDS equation, let us take entropy to be a function of temperature and volume. Then we can write ds as delta S by delta T at constant V into dt plus delta S by delta V at constant T into dV. Let us multiply the above equation by T, because what are we finding? We are finding the TDS equations, so we have to multiply by T. What do we get? TDS is equal to T delta S by delta T at constant V dt plus T delta S by delta V at constant T into dV. Call this equation 1. For a reversible process, TDS is equal to dQ. So we get T delta S by delta T at constant V is equal to delta Q by delta T at constant V is equal to CV. Also, because we are studying the Maxwell's relations applications, we have to use the Maxwell's relation. So we get delta S by delta V at constant T is equal to delta P by delta T at constant V. Using equation 2 and equation 3 in one, we get TdS is equal to CV dt plus T delta P by delta T at constant V into dV. This is the first TdS equation. Let us see its application in the case of van der Waals gas, which is undergoing an isothermal expansion from volume Vi to Vf. And then let us find out the amount of heat transferred. We have just seen what the first TdS equation looks like. The van der Waals equation is P plus A by V square, V minus B equal to RT. Rearranging this equation and differentiating with respect to temperature at constant volume, we get delta P by delta T at constant V is equal to R by V minus B. For an isothermal change, dt is equal to 0 and the TdS equation becomes TdS is equal to RT by V minus B into dV. Hence, we are able to calculate the heat transferred, which is nothing but RT log of Vf minus P by Vi minus P. So, this is the first TdS equation and its application. In my subsequent lectures, I will be discussing the various other applications of the Maxwell relations. I hope you've understood the lecture and hope to see you in my next lecture also. Thank you.